So, now let us focus on what is the kind of stuff we are going to study in this course, and it has been called problem solving using search or search methods for problem solving. So, let us understand what we mean by problem solving. So, let us start with a popular sport on a football field. Let us say that you are a striker as shown in this figure. So, there are two teams, the blue team and the red team, and you are the striker for the blue team. You have the ball, and at every instance you have to make some decision. So, in some sense at every instance you have a problem to solve and you have to make some decision. So, you are there with the ball, you are moving towards the opponent's goal, and the opponents are closing in. Obviously, they would run towards you, try to snatch the ball from you. What should you do in this situation is the question. And when we talk about problem solving, we say that an autonomous agent in some world has a goal to achieve. So, this goal is nothing to do with the football goal. A goal in the sense as some desired state of affairs has a goal to achieve and a set of actions to choose from to strive for that goal. And the task of the problem solver is to decide as to what actions that the problem solver would choose. That is what we understand here by problem solving. So, on the football field, an intelligent agent would pass the ball to a teammate who is free and then who has a much better chance to score the goal. So, this is a kind of decision of that this player has made, and of course, it is a decision in a multi agent scenario, and 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 clearly an intelligent footballer would do something like that. In fact, they are trained to do something like that, set pieces as coaches tend to call them. But this is the kind of thing that we are talking about problem solving, that you are in some world and you have certain goals to achieve. You can perceive the world, you can act upon the world, but there may be other events happening. So, for example, it might be raining outside or things like that, and there may be other agents also doing things essentially. For example, a shopkeeper may be opening a shop, closing a shop, and you want to go and buy something, you have to keep their actions in mind also. But the real world is in that sense quite complex. It is not that we can perceive the entire world completely. Our knowledge about the world is always incomplete. We can even while I am sitting and recording in this room, I cannot say whether it is raining outside or not raining outside. I can't see that. Our actions can also be quite complex in the sense that uh, they may or may not work in the real world essentially. So, you may rush towards towards the railway station in the hope of catching a train, but you do not know whether you will be able to catch it. So, one must learn to walk before one can run, deal with simple problems first, and that is why what we will study in this course will look like simple problems, but they often have insights into how problems can be solved. We will assume that the world is static, that nobody else is doing anything, we are only making the decisions in the world. Of course, that is not true. None of the assumptions that we are making are true, but we will start with that. The world is completely known. We will assume that everything that is to be known about the world is known. Only one agent changes the world, that there is one problem solver who is doing it. In the real world, of course, as we saw in a football team, there are other players, there are teammates and there are opponents and so on. The only place where we will see multi-agent scenario is in a game like chess, where there will be two players involved. Actions never fail essentially. So, we assume that whatever actions we plan to do will work essentially. If you have played basketball and you have had the intention of throwing a ball into the basket, uh, you would know, or at least many of us would know, that it does not always go into the basket essentially. So, actions may be intended, but they do not always work. So, in the real world we have to monitor the execution of our actions, but that is a different thing altogether. And finally, the representation of the world is taken care of. We will assume that we are not going into the intricacies of representing the real world and solving problems in the real world, which is why we would look at simple problems too, which are easy to represent. And that is one of the reasons why games like chess were very popular as work to be done in AI, because it is very easy to represent the chess this thing, and the move is very easy to describe, and the move is very easy to make, unlike football, which is much harder. So, humankind is a problem solving species, and essentially we adopt two approaches to problem solving. On the left, you can see in this shaded circle the kind of problem solving that we want to study in this course, which is sometimes called as model based reasoning, because you have a model of the world and you are reasoning on top of that. But what distinguishes it is the fact that this is reasoning by first principles, and by first principles we essentially mean trial and error approaches or search approaches. We just try out everything and see what works and what does not work. On the right hand side, you see a knowledge based approach. Humankind, of course, is a very knowledge intensive society. Not only do we learn from our own experience as we are growing up, we learn from others, we learn from books, we learn from teachers, we learn from YouTube and all kinds of stuff. And we store all this experience in some manner and reuse it to solve problems. So, you never want to reinvent the wheel in some sense. That is the motto of experience based problem solving or memory based reasoning, that never, you do not want to reinvent the wheel. If you know how it is to be done, just go ahead and do it. But if you do not know how it is to be done, then you must use first principles. So, in some sense, we are going by the fact that you never step into the same river twice. So, every problem in some sense a new problem, but that is not really true, because we do reuse lots of experiences. If you have learned how to make a good cup of coffee, for example, you do not try to figure out from first principles every time you want to drink coffee, you just know how to make it. So, in this course we will focus on search methods, which are the first principles methods, and I have a companion course called knowledge representation and reasoning, in which we look at how to represent knowledge and reason with that. It is not even a course on memory based reasoning, where we have actually a third course, but I am not offering that at the moment. So, just to illustrate this example of search versus knowledge, Rubik's cube is a classic example. All of us must have seen it at some point of time, essentially. Okay. And it was invented in 1974 by Rubik, who was an architect and a designer. And since he invented that, we have been, millions of us have been engaged with solving the cube. But what is the current scenario? You give this cube to a kid and the kid will solve it in a matter of few minutes, essentially. Everybody knows how to solve it. This illustrates a knowledge based approach to solving problems, which means that somehow we already know how to solve the cube, and we just do some kind of pattern matching with the given cube, and we know that with this pattern this is a move you should make, and so on and so forth, and people can solve it very quickly. But if you do not know the solution, then you would do trial and error or first principles methods to solve it, and that is what we are going to explore in this course. There is an article on how a new deep learning algorithm solves a Rubik's cube all by itself, and in this article, if you go to this link, you will see that Rubik himself took 1 month to find the first algorithm to solve it. And this is reminiscent of the fact that when I was a young student, when the Rubik's cube just came, and everybody on earth was fully kind of engrossed in trying to solve it, and the solution had not been spread so far, and people were trying to solve it from first principles, and people were losing night after night of sleep trying to solve it on their own. So, as this article says, Rubik himself took 1 month to find the solution. Of course, designing the cube does not give you any insights into how to solve it, that he had to do independently. So, there is this article talks about this deep reinforcement learning approach that was used to find efficient solutions without any human guidance. So, this whole idea of reinforcement learning is to try to do away with human guidance, essentially. Earlier form of learning that we said deep learning was that you give labeled examples. This is the image, this is the class label, this is the image, this is the class label. Reinforcement learning does away with this human inputs and tries to learn from first principles by itself. And there is a post by in NVIDIA which talks about this algorithm. Here is another example where we can use search and reasoning both. most of us would have tried their hand at Sudoku at some point or the other. So, I presume you are familiar with the puzzle, uh, but you can see that there are 81 squares here, and you want to use digits from 1 to 9, and the digits must only one digit can be used either in every row or in every column or in every smaller square of 9 circles. So, 1 can be used only once, 2 can be used only once, and so on. Typically, the puzzles which appear in newspapers are something like this, that it is a partially filled uh, Sudoku, and you have to fill the rest. Now, search of course would be a simple approach. Just try out all combinations of, if I put 1 here, if I put 2 here, and so on, will it work? But most of us try to do some kind of reasoning. So, this kind of reasoning is different from solving problems using memory. This is trying to do some kind of making inferences about certain things. So, we might say that I can see 5 already in the first row. So, it cannot be in the first row in that last square on the top, last sub square on the top. It is also in the second row. So, it cannot be in the second row also. So, all those red crosses says that 5 cannot be here, because the rule says that in every row it can occur only once, likewise in every column, and at the end of it we are left only with one place for 5, and therefore, we can just directly write that part of the solution there. So, we can do this sort of a thing again and again. So, we can see for example, here that 8 cannot be here, and because 8 is here, it cannot be here. So, there is only one place left for 8, and we can write it there. So, this kind of reasoning we can do. Another form of reasoning that people often do is that they look at a particular square and say what can go into that square. So, if you look at the column, you can see that 5 cannot go, 8 cannot go, 6 cannot go, 4 cannot go, 7 cannot go. And if you look at the row, you can see that 4 cannot go, 1 cannot go, 9 cannot go, and 5. So, they may narrow down the search, and they say, okay, this must be either 2 or 3. So, many people solve it like this, that they try to narrow down the options and do that. So, it's you can see that the second approach that I talked about is a kind of a combination of search and reasoning. You are trying to still do searching, that can I put a 2 here, can I put a 3 here, and so on, but you are also narrowing down the domain in the sense that for this square you can only put a 2 or 3, and then I may continue searching, and then supposing I fill up a 2 or 3 in this square, then I will narrow this down, and so. So, this kind of combination of search and reasoning is very easily captured in this area of constraint satisfaction, and we will try to see that towards the end of the course. That is the last segment. So, our focus is going to be on problem solving, and our focus is going to be on search, but there are other things that we do in problem solving. So, we for example, do knowledge representation and reasoning, and typically we use the language of first order logic for doing that, because it allows us this whole deductive machinery that logicians have built over a period of time. But I also said that reasoning is not necessarily deduction, it can be other forms of reasoning like plausible reasoning and maybe abduction, uh, which maybe we will be able to talk about it later. And of course, logic and search gives us a mechanism for doing logical deduction, and if we get time towards the very end of the course, we might try to look at how deduction is done as search. But otherwise, we see that this kind of reasoning, deduction as well as search, they are all subsumed by constraint processing. Apart from that, as we said, we can use memory to solve problems. You can populate your agent's memory and reuse those cases, as we call it, and that is the whole area of work which is very successful commercially, called case based reasoning. We are not going to study that here. Or we can do some kind of machine learning. Once you have done case based reasoning, populated the memory, you have the data available, and you can use machine learning to do various things. So, we can use it to learn rules, for example, as we do when we construct decision trees, or we can use that data to learn neural network models, as we have already seen a glimpse of that. So, we can separate these two kinds of approaches in two ways. On the top left is the first principles approaches, on the bottom right are the knowledge and experience based approaches. And again, I would emphasize that in this course we are focusing on the first principles approaches. So, here is a problem I want to leave you with. You must be familiar with this map coloring problem. You have a set of regions. So, if you have seen a school atlas, you would know what we are talking about here. So, we have a certain set of regions A, B, C, D, E, and let us say in this problem, for some reason we have decided that each region has a preferred set of colors. So, A for example has the color blue or green, B has red, blue or green, C has blue or green, and so on and so forth. Each region has a preferred set of colors, and the task is to assign a color to every region, such that no two adjacent regions have the same color essentially. So, you have seen school atlases have like this essentially, if you look at the map of India, Maharashtra will be shown in one color, Andhra Pradesh would be shown in a different color, and so on. This map coloring has been of interest to mathematicians for a long time, and there was a conjecture that any planar map, by any planar map we mean any map that can be drawn on a two-dimensional surface like this one for example, that there are four colors are enough to color any planar map, whatever the shape of the regions may be essentially. That was called as the four color theorem. It was not proved for a long time, but it was proved by a computer program not too far in the past. How would we address this problem? That's something that we want to look at in this course. And so, typically we do not draw maps like regions and pictures like this. What we do is we represent it as a graph, which in this case is called a constraint graph. So, there are these 5 regions which form the 5 nodes in this graph A, B, C, D, E, and each node has a set of labels that can be used to label that node, and there is a relation between certain cities which are touching each other. So, for example, A and B are touching. So, there is an edge between A and B in the graph, and it is labeled by the nature of the relation, which is that the value of A is not equal to the value of B. This kind of a graph is a constraint graph, and constraint processing would say, okay, you give me a general constraint graph and I will try to find a solution for that. We will look at general purpose algorithms to do that. We will do that towards the end of the course. So, with this I think we come to an end of the introduction, and we start next with search methods. We will start with simple search algorithms like depth first search and breadth first search that you must be familiar with, but we will quickly move on to analyzing them and looking for more efficient methods. So, we will do that next.